Thank you, Caitlin. Good morning and happy Earth Day. My name is Ian Reese. I'm an environmental education assistant at Kentucky State University. And I'm going to get us started today talking about a brief history of Earth Day and climate change. So 2021 marks the 51st Earth Day celebration in the United States. So Earth Day is celebrated every year on April 22nd. And Earth Day started as an idea at a UNESCO conference in 1969. A guy named John McConnell proposed a day to honor the Earth after witnessing an oil spill in Santa Barbara. So shortly after that, Senator Gaylord Nelson, with help from an activist, Dennis Hayes, organized a nationwide environmental teach-in to be held on April 22nd in 1970. And so that teach-in grew and became what we know today as Earth Day. And so this picture on your left here is a picture from the first Earth Day celebration in 1970. So 51 years later, Earth Day has become a global celebration, celebrated all over the Earth. And it's organized by an organization called earthday.org. So they've kind of become the authority on Earth Day all around the world. And so they've assigned a theme for 2021 as Restoring Our Earth. So restoring our Earth to natural system processes and emerging green technologies to restore the world's ecosystems and forests, conserve and rebuild soils, improve farming practices, restore wildlife populations, and rid the world's oceans of plastics, as well as to bring hope to a world impacted by COVID-19. So what are the impacts that necessitate restoring our Earth? And those impacts would be climate change. So what is climate change? Climate change is a very broad topic that encompasses a lot of different processes and phenomena. So climate change is a long-term change in the average weather patterns that have come to define Earth's local, regional, and global climates. These changes have a broad range of observed effects that are synonymous with the term. So it's very important that we distinguish that climate is not weather. When we talk about weather, we're talking about day-to-day, whether it's raining, whether it's sunny, whether it's hot. And when we talk about climate, we're talking about long-term, many months, over many years, average conditions. And so now we'll talk a little bit about the causes of climate change. So I'm sure some of you may have heard of the greenhouse effect. So increased greenhouse gas emissions cause an expansion of the greenhouse effect. So the greenhouse effect is a natural process that regulates Earth's temperature. The greenhouse effect is a natural process that regulates the Earth's temperature, and it's driven by greenhouse gases in the atmosphere. So these gases, significant ones that we're concerned about include water, H2O, methane, CH4, nitrous oxide, N2O, and of course carbon dioxide. So with increases in CO2 and these other gases in the atmosphere, we're causing a greater and expanded greenhouse effect, which is warming the Earth. So energy comes from the sun. If you look at my diagram here, there we go. Energy comes from the sun down to Earth, and some of that energy is reflected back out into space, and some of that energy is absorbed into the Earth's surface, and that energy is released back into the atmosphere as heat. And so those greenhouse gases act as a blanket, keeping that heat trapped in Earth. And so right now we're seeing an excess in mostly CO2, but also all of these greenhouse gases. And this excess CO2 is primarily the result of burning fossil fuels. And so how do we know this is happening? How do we know that we're seeing an expanded greenhouse effect? How do we know that the climate is changing? And we see that through things like global temperature rise, ocean acidification, sea level rise, a warming ocean, shrinking ice sheets, glacial retreat, decreased snow cover, and extreme weather events. And a lot of these topics we're going to talk about throughout the day with our guest speakers. And so this is a video. I'll try to explain what's going on here before we play it. This is going to show historical CO2 levels in the atmosphere. So starting out right here, this is going to go through time, and you'll see actual measurements over here in real time as we go across, and then you'll see the graph starting right now from 1980 all the way up to 2019. You'll see the graph of atmospheric CO2. So I'm going to play the video. So starting back in 1979, we're looking at carbon measurements. It was about 336 parts per million. And if you look at the graph on the right, you can see a steady rise in CO2 emissions. And you can see the up and down cycle. That's the annual cycle of CO2, with the average being the entire graph. And all those dots on the world map that you're looking are where these measurements are coming from. So these are actual measurements of CO2 being made in the atmosphere. So in October of 1989, the observatory at Mauna Loa in Hawaii sees 350 parts per million for the last time. So from then on, we've always been above 350, continuing to rise. So now we're entering the 2000s. And we're approaching 380 parts per million. And as we approach the 2010s, getting closer to 2020, we're reaching 400 parts per million. So within 30 years, we've gone from about 335 parts per million to over 400. And so in 2019, we reach about 412 parts per million. Today, we're sitting at 416 parts per million. So we're going to go back in time a little bit using Keeling data to expand this graph. And then we're going to go back farther in time using historical data. This data comes from ice core samples. And so using ice cores, we can sample ancient atmospheres of Earth. And so back into the pre-industrial period, we're sitting at about 278 parts per million. And then we go back even further, up to 800,000 years ago, up to the time of the ice ages. And back during the ice ages, atmospheric CO2 was at 185 parts per million. So you can see, looking at this graph, that CO2 currently in the atmosphere has never been higher than it has in the past 800,000 years. And so that is the concerning part of increased CO2 in the atmosphere. And these are some data sources from the video. All right, so now we need to talk about why that's important. Why do we care that CO2 is increasing? And so some global impacts, we'll see increased temperatures, we'll see a lengthened frost-free and growing season, which at first glance you might think that's not so bad, but we'll talk about other impacts that may negate that. Changes in precipitation patterns, more droughts and heat waves, hurricanes will become stronger and more intense, sea level rise. The sea level will rise 1 to 8 feet by 2100. The Arctic is likely to become ice-free, and also the problem of ocean acidification. Caitlin will talk about ocean acidification shortly. All right, so you may think, well, that's really terrible. You may have seen, images of a polar bear on a melting iceberg, and you may think, well, that's sad, but what does that have to do with me? And so let's talk about the local impacts, local to Kentucky and the southeast region. So in the southeast, that's from East Texas to the East Coast and Kentucky South, we'll see sea level rise posing a widespread and continuing threat to the region's economy and environment. That's mostly a threat for coastal cities, but if people have to start moving because of increased flooding, that's going to affect inland areas as well. Extreme heat will affect health, energy, and agriculture. A decreased water availability will have economic and environmental impacts. So more specifically, we can start to look in Kentucky at what we're facing. So for precipitation and water resources, we're going to see an increase in annual precipitation. We're also going to see rising temperatures, which increase evaporation, which dries out soil and decreases runoff to rivers. So the evaporation offsets precipitation, leading to decreased recharge rates and strained water resources. So what we're going to see is more frequent droughts, and while we will see more rain than in previous years, it will be in larger rain events, and they will be more sporadic. So it's going to be a lot less easy to predict rain and precipitation patterns. So for aquatic ecosystems, warmer water, of course, lowers dissolved oxygens, increasing the frequency of algal blooms. You may have heard of algal blooms. They can be toxic to the wildlife and to the drinking water. Flooding, navigation, and hydroelectric power. Flooding and heavy rainstorms are becoming more severe. You'll learn more about this later today. Longer and more severe droughts could impact river transportation and hydroelectric power production. There are some hydroelectric power stations that are already reporting decreased production due to unpredictable river conditions. Agriculture. So longer frost-free growing seasons and increased concentrations of atmospheric CO2 may increase yields. However, if you pair that with severe drought and more hot days, you're likely to get an overall decrease in yields. Western Kentucky is especially vulnerable to these increased hot days. And then higher temperatures, of course, are likely to decrease livestock productivity. And our forest resources. Forest cover likely will be unaffected, but the composition may change, so we may see changes from, for example, maples and beeches to more oaks and hickories. Droughts reduce forest productivity, and there's a possibility for increased insect and disease threats due to the changing temperatures that may favor insects and diseases that we haven't seen before. And so another impact of climate change, of course, is human health. So we're going to see a worsening of the urban heat island effect. And if you don't know what the urban heat island effect, that essentially says that the more urban area, the more urban land cover that you have, the hotter those temperatures are going to be. So if you have built up cities, they're going to be significantly warmer than, say, a forest or even a grassland. And prolonged high temperatures have multiple negative human health effects, including dehydration and heat stroke. Higher temperatures can increase ground level ozone, which is a key component of smog. And ozone can also aggravate lung diseases, among other health effects that come with that. And I want to show you this screenshot from the Louisville Heat Island map. If you go to this website here, you can access this, and it's actually interactive, and you can play around with it and click on different areas and see the data from those areas. And what you'll be able to see is that in the built-up urban environments, there's much more heat than in the more suburban or less developed areas. And so what do we do now? So we've talked about all these problems, and what are the ways we move forward? And so when you're talking about climate change response, there are two main approaches. The first one is mitigation. So that involves reducing the flow of heat-trapping greenhouse gases into the atmosphere. So that's reducing our CO2 emissions and other greenhouse gas emissions. That can also look like planting trees and reforestation efforts. So the goal of mitigation is to stop the effects of climate change before they happen. And the other approach is adaptation. So this is adapting to life in a changing climate. So this involves adjusting to actual or expected future climate. So adaptation is all about resiliency and being resilient in the face of a changing climate and trying to live with the effects of a changing climate and try to decrease the damage done. All right, so climate change is a very broad and complex topic. There's a lot to talk about, more than I could talk to you about in 20 minutes. But stay tuned for further presentations and discussions concerning climate change throughout the day. I'm going to leave you with some key terms to think about throughout the day. Climate change, weather, greenhouse effect, global warming, anthropogenic, urban heat island, mitigation, and adaptation. So thank you for attending our Earth Day celebration. My name is Ian Reese. You can contact me at ian.reese@kysu.edu if you have any questions.